Hello, everybody. Yeah, I'm happy to be here and to tell you about developing software at RVU, the company Henning just presented. And yeah, I hope it's interesting for you to hear what we do, why we do it, and how we do it. Because this is streamed, I will use the laser pointer. And the abstract of the talk, I think you read it when we initially constructed our object-relational mapper, the ORM, in about 2009. We were limited to the C++03 feature set. And despite these limitations, we achieved most of our goals. During the following decade, we continuously improved and extended the ORM to achieve better usability, prevent errors, and increase performance. And some new C++ features introduced with the following standards helped us with this effort. The talk will give an overview over what we did, why, and how. Parts of it, because covering everything would take much longer than is planned for today. And I will also illustrate C++ features we still desire. Who I am? I studied computer science at Technical University in Berlin and worked in network security before joining IVU Traffic Technologies, and I've been working there since 2004. Currently, I'm a senior architect in IVU Vehicle. You saw the slide, but maybe you don't remember. It's in the middle where the vehicles are dispatched on the trips they are going to do. And as a C++ expert, one of my focuses is on exploring modern C++ language features to achieve good performance and high quality. And if you have comprehension questions in between, please ask. Discussion we should do at the end. And sorry, I do not have the time to explain everything about ORMs, so bear with me that some things are very condensed. Okay, let's go. The system. IVU Plan is, as Henning already said, an enterprise resource planning system for public transport companies. It has about 6.8 million lines of code in C++, and that's not counting empty and comment lines, so that's code. It has 3 million lines of code in Java and about 700K lines of SQL code. We have more than 700 tables in our database, and the system has been developed since before the year 2000. So it's an old system. But it has been continuously extended and refactored. So that's not that big problem as it sounds. To give an overview over the system structure, it's a classical 3-tier architecture. In the bottom, we have the database tier, and then we have the middle tier from the data containers up to the business logic, and then the presentation logic, the third tier on top. The data containers provide data structures for table rows, and they are generated from annotated database metadata. We do that primarily to achieve type-safe primary and foreign keys. Other than that, there are simple data types used, the types the database knows about. Above that, we have a database access layer, the basic database access, and that enables type and structurally safe load and save for the data containers below. And above that, we have an enhanced layer to allow for the type-safe construction of select statements together with their where conditions, allowing to dynamically assemble queries at runtime while preserving correct bind variable assignments. And then the part I want to talk about next is the object-relational mapper, which allows building a graph of business objects and traversal of edges on one-to-one relations and to many relations. And the ORM also maps simple to elaborate data types and provides for efficient load and save. Above that layer, we have the business objects, which are implemented using the object-relational mapper. And the business objects contain those parts of the logic pertaining to a single business object and all objects reachable from there. So our philosophy is a navigatable object graph and not a service-oriented architecture. Above that, we have data access objects, which bundle all database access strategies which belong to a certain business object class. And above that, the business logic implemented in services and business objects. The object-relational mapper itself, here counted together with the transaction context, has about 120 klog in header files. So you can see it's mostly implemented in templates. And we have a 12 klog CPP, so some parts are not templates, but only 10%. And if you look at the layers which use the object-relational mapper, it's about 1 million lines of code. So the ORM is just a small library used by a large business logic. Okay. The ORM, difficult word. What does it do? It allows to retrieve graphs of objects from the relational database tables and allows to navigate this graph of objects in memory. You can change object properties or references between objects on the objects and then save the objects back to the relational database. To do that, we need to declare a mapping from the tables and columns to objects and data members. And then we want to define interfaces for the objects with elaborate data types not existent in the database. So we have value types for length, mass, volume, speed, and anything else. And for example, constraint strings like trip numbers. We talked about the business we are providing. So they have special requirements on the format of trip numbers. So we don't have simple strings there, but elaborate data types, enumerations, and other things are mapped on the interface of the objects to the database tables. For the IVU, the goals were longevity first, at least 20 years. I said we started developing the software before 2000, and so we are looking at very long life cycles, so the ORM had to provide this kind of longevity. And therefore, it needs to be easily maintainable, and the technology which we are basing on should be available for a long time. We also need very, very good performance, together with good scalability, because we have many objects, large sets of children or referenced objects, like customers having 10,000 vehicles, 200,000 trips a day, 10,000 network points like bus stops or tram stations. at the same time, we want to achieve ease of use. So when coding with the system, we want a minimum amount of boilerplate code. It should be easy to learn and to apply, and it should result in a very low user error rate, at least 1 million lines of code. And we needed to have this new system work in conjunction with the old code. And also, using templates, can result in long build times. So that was also a goal, to keep the build times acceptable. We took inspiration from J2EE, Java 2 Enterprise. What does it mean? Whatever. And it has services, service registration, service injection, business objects, data access objects. And then it has Hibernate, which is one of the the most prominent persistence provider in Java. And it delivers object-relational mapper, business objects, or the facility to build business objects. And these technologies rely heavily on annotations and reflection. C++ has no reflection, yet, I may say. And it has no annotations. So what do we use instead? We used, and we are still using, type defs, templates, member pointers, member function pointers, and static methods to provide the meta information which is provided via annotations and reflection in Java. Okay, so just a small example. Here a little graphic illustrating a very, very reduced part of a traffic network. You get network points like bus stops or tram stations, and you get a link between the stations, and these are directed links, so it's a bit senseless because you can only travel in one direction and you can't get back, but for example, in this context, that should suffice. And I have brought 4 classes, 4 business object classes, a network point, a link, a stop post name, and a division. Division is like the bus division, the tram division, the rail division of a public transport company. And how are business objects structured? They have flat attributes like a name or abbreviation, and as it is stored in the database, they have foreign keys, and these foreign keys reference other objects, like this division, the network point, the data, the row in the database of a single network point references the division it belongs to. And therefore, we need reference attributes because we want to be able to navigate from the network point to the division. So we have a type reference to 1, which is mapped to a certain foreign key in the database table of network point, and it can be resolved to the division object. And that's a to-one relation as annotated here. We have reference to many relations, which are these, annotated with n, and in the database they are modeled by inverse reference directions, because the link has the foreign key to the network point, but in the object model we want to reverse the direction. We want to go from the network point to the links which arrive at that network point, or to the links which depart at the network point. So the reference direction in relational database is inverted, and so the relation needs to be mapped to the foreign key of the reference row link in that case. And for the stop post name, we have the parent to children relation, which is a subclass from reference to many, and it adds the management of the ownership on the parent object. So when a network point gets assigned a new stop post name for a certain usage, like traveler information system, there you want, maybe the public transport company wants to display a different kind of string, then for another usage you can add a stop post name, and this stop post name is a record in the database which belongs to the network point, and it has some kind of ownership. There's some kind of ownership relation between the network point and the stop post name, and so the network point is the parent and the stop post names are the children, and so we have the ownership management as additional feature in the reference. So when we add a new child, then the child's parent reference is automatically set. Okay, so how we put that into C++ code. So I brought an example. For the network point, we have a structure which contains all definitions for references on the network point. And for example, we have here a constraint foreign key reference division ref, which lists the referenced object type and a reference, well, an ownership, technical ownership attribute, which is weak, which means the object held via a weak pointer and not via an owning shared pointer. In contrast, the strong relationship type means that the object is managed by a shared pointer, so to reflect the ownership relation in this case. So we have the constraint fk. Fk stands for foreign key. The foreign key reference constraint because the database has a constraint which enables, which disallows dangling references, and this is reflected in this name because the behavior of the framework changes upon having this constraint. And we have, for the stop post names, we have an inverse foreign key reference to the class stop post name, and the parent is the network point, and it's a to many reference, and it's managed strongly, so it's kept with the shared pointer. The third type of reference we have, it's also a reference to many, like the stop post names, but here we have two references which are, from their parameters, are equal. They both go from link to network point. It's a to many reference, and the reference type is weak. But we have two different kinds because we have the arriving links and the departing links. And to be able to separate those two, we use tagging, type tagging. So we define empty structures just to have a type, and we put them here to be able to discriminate between the arriving links reference and the departing links reference. And how it's used, we'll see later. Okay, example business object. How is the network point implemented? It inherits the refs definition, but that's not very important. It's to ease the access to the definitions, but it's not strictly necessary. I have omitted the derivation from the interface in this example. You need to put it there in your head. Okay. I hear the speakers. Okay. So in the private section, of the network point impl of the business object implementation, we find the reference to 1. And here it uses the division reference, which we defined on the previous slide, contained in this network point refs structure. We have super, which is a shorthand for the superclass, which we define in the standard base class, which I omitted from this slide. Maybe I should add it, but I forgot. And we have, this is interesting, we have something here. It's a DC network point FK division. And the comment says, gives a bit of explanation. The DC is a shorthand for data container. You remember this is the level directly above the database, where the rows are just, the database rows are just put into C++ structures or classes. The FK stands for foreign key, is an abbreviation for foreign key. And the DC network point is code generated from database table structures and meta information about the mapping. So we have a base level of mapping from database tables, table structures to C++ data structures, but these are plain mappings, but they contain already type-safe foreign keys. So this foreign key is a global static in the DC network point class, and it contains all the information about this foreign key. So from which table to which other table, how the column is named and stuff like that. And so we can define the reference to 1 just like that. It's not as smooth as annotations, but it's very close. So we have a member variable division. So if you want to access this division, we implement just a getter, for example, get division, and this division getter just forwards to this member variable and calls the get method. And interestingly, it provides itself as a parameter. And this giving this as a parameter, allows for the reference to get to the information it needs, namely the value of the foreign key. Because the value of the foreign key is contained in the data container. The data container is a member, not shown on this slide, of this network point impl. And because the reference needs the information which key to resolve when get is called, it needs a back reference to the business object. Okay, that's one of the tricks we did. Because we avoid making the reference dependent on the network point impl in a way which needs to be initialized on construction and would take up space in RAM. So it's just dynamically given with each call to the reference. We provide the network point impl. And reference to many look quite similar. In this case, we don't have the foreign key because the foreign key is already contained in the reference specification. Okay. And these getters are implemented similarly, just here, symbolized by the 3 dots. You can imagine how this is done. And parent to children is a bit more complicated. It's like a reference to many, but it also has the information about the implementation of the child. And this is also interesting, it has a member function pointer which allows the reference to set the network point, the parent reference, on the stop post name when the stop post name is assigned to a network point. So that's also a pattern we used member function pointers as non-type template arguments. Okay, how is the reference to one declared? It's just the template. It has the reference tag as a parameter. It has the standard business object impl as a parameter, or this concrete business object impl, which needs to derive from standard business object impl, therefore the name. And then we have this complicated looking expression. It's a foreign key implementation depending on several types which are extracted from this parameter before, and it's just a const ref on this foreign key global static variable. Or no, it's a static member of the data container. And we have some defaulted variable here, parameter here. That's not important at the moment. Okay, so what we see is we use non-type template arguments, especially references to global statics, though it's class statics, but they are globally reachable, so they are kind of global. We could not use auto for non-type template arguments because it's a recent addition to the C++ standard. We had C++03, and that caused the requirement to give this parameter, because we need this parameter only to be able to specify this type here. If you could write auto in this place, we wouldn't need that parameter. So future work would be to convert these things to use auto for non-type template arguments. We could do that because it would allow us to drop other template arguments, standard BO impl in this case, but it would not help us because it would not help us that much, because the congruency requirement would still be there, because this foreign key has to match the type, the DC type, the data container type, which is used in this business object class. And to prevent long template error message storms in the compiler output window, it would then be quite nice to use concepts to prevent that and to have better error messages. And when I look back at the time I implemented that 12 years ago, I had a lot of compiler crashes because the tools were not very stable, and if you had mismatches here, the compiler would just cease to work and say internal compiler error. And it was a bit tricky to get all these things to run, but it wasn't that hard on the other side, so on the other hand. Okay. Now another trick. You've seen the getter. The get needs to get the referenced object from somewhere. So how can a reference fetch a referenced object? Where should it get this object from? Or a vector of referenced objects? They need to come from somewhere, because the fetch is triggered when calling the get, and the reference is not resolved. And as you have seen, it's always forwarded from the referencing object. Yeah, we also have prefetching now, but we try to stay simple. So when the reference gets the get call, the get is called on the reference, it needs access to the data access object, because the data access object is the only place in the system where we can retrieve an object by giving its primary key. So the data access object provides a find by primary key. And so we need access to the data access object. The ID type suffices. We can just select the proper data access object because the data access object is type specific. We have one data access object for each business object class. That's the difference to the Java world, but it's easier for us. And some inverse references need type tags. We had seen this for arriving and departing links to separate them. I will show how that works in a moment. But first, let's talk about where we get the DAO from. Because all information we need must be in the referencing object itself. Because the only thing we have is the business object, and we call get. So we need some kind of context. And to put a pointer to a specific data access object into each reference would be very expensive in RAM and setup cost, so we didn't do that. Instead, we wanted to use one pointer to a component-specific entity resolver object in each business object, and this entity resolver should be able to demultiplex the call, the find call, which is typed by its ID. And to produce such an entity resolver, the first entity resolvers we wrote by hand, but it became very quickly very tedious and error prone. So we devised a way to synthesize entity resolvers. And we do that by listing all access types needed for all references in the respective component. What this means, we come to that. We have a standard access by ID. It's like find by ID, and the ID type selects the data access object, and the access is just a forwarder to the proper data access object. And we have to bind special access methods by foreign key depending on the reference tag to a specific data access object method. Okay, the access definition maps a reference tag to a specific finder, and it does that like so. So we have, for example, the link access, and it's defined as a generic access on the link DAO, which provides the standard find methods, find by ID and find by set of IDs. And we have some special accesses. And here you see the arriving links reference tag is bound to the find arriving links method in the link DAO, and the departing links reference is bound to the find departing links DAO. And here you can see, again, we're using member function pointers as non-type template arguments, and we define a type, which is the link access. And then we produce a resolver, and the first attempt was C++03, a resolver chain. We didn't have parameter packs or variadics at that moment, so we used a recursive template, and the recursive template resolver creator chain gets the first access, and the second parameter is again a resolver creator chain, and it gets the next access, and so on and so on and so on. And you can imagine getting a lot of closing angle brackets in the last line when there are many accesses needed in a resolver. And this resolver chain produces a chain, an inheritance chain, starting with the base class, which is the default parameter for the second parameter omitted here. And then we just have the resolver creator chain, abbreviated as RCC here, and it inherits from base, and it uses using base find by ID. So we need to seed it here. It's like we never use this signature, but we need it because we want to have using on the base class. So we have to have the signature here, and then we pull it down, and we implement find by ID with our specific ID in this access, and then we inherit, and we have a resolver creator chain division access, which has this as the second parameter, and then it inherits from its second parameter. It has the using, it delegates the using to the top level, and then implements its specific finder. It works. It results in very long type names and many intermediate types, but it works even with many accesses. But the overload resolution needs to traverse the chain until it finds the match. Yeah, sometimes to get build times down, I wished I would have been able to profile the compiler itself. Okay, then came C++ 17. Well, first came C++ 11, and we had variadics. And then I said, well, that's the nice thing. We should convert the resolver chain into a variadic implementation. So producing a variadic resolver where we just can list the access classes as sequence, comma-separated sequence. Looks very nice and produces this kind of inheritance hierarchy. So we have only one class, and it derives from all listed base classes here. But there is a problem, because the first try to convert it to a variadic template failed, because variadic using was not available in C++ 11. And without variadic using, I could build this inheritance, but I could not overload in the derived class, because these would not be visible. Okay, so I had to wait 6 years until C++ 17 solved the problem with variadic using, and now we have variadic using, and the implementation becomes very simple. Okay. For an example, the traffic network components resolver has 110 access classes in the variadic resolver. Before Visual Studio 2017, we always got this C4503 warning because the decorated name length exceeded 4090, I don't know, 3 characters or something like that. Luckily, Microsoft dropped this warning in Visual Studio 2017, so this is no longer a problem. And the conversion of the chain into a flat multiple inheritance reduced the binary size by a lot less than I expected, 0.5 to 1%, and the compilation time became a bit shorter, but not really that much. But it looks nicer now. Okay. Let's talk about transaction handling, state transitions. I don't want to dive deep into transaction handling, but when transactions start and transactions end and objects get saved, we had the need to do similar things on all references, just to make the state transition. Before save, we needed to do something. After save, we needed to do something. Just notify all references. Oh, your object has just been saved. And then they switch internal state. After end of transaction, we tell them you can't resolve anymore because the transaction has ended. So these state transitions we need to apply in the same way on all references. Okay? Reflection. If we had reflection, we would have used reflection. But we didn't have reflection. We don't have reflection yet. So we implemented something I call reflection for the pool. And that's a static method, in this case called getReferences, and it returns a reference description list. And what we need to do is fill this, implement this method. And yeah, okay, I show how it's implemented in a moment. This is a reference description where the virtual functions for these state transitions are listed, like update, pre-detach, uninitialize, notify saved. And this is also a pattern we use very often, is combining templates and pure virtual methods. Like it's a template on the business object type, implementation type, and this defines an interface. And when we construct the reference description list, we add, oh, what's that? A member pointer. Okay, so we use a member pointer to specify the reference, and we list all references contained in the object. So now we got reflection for the poor, because now we know what the reference members are contained in this implementation. Okay, and then we can just work on all references. In theory. In theory, there is no difference between theory and practice. In practice, there is. Guess what happens? What happens? The getReferences method is not updated when a reference has been added. Standard error. I have a reference. I can use the reference. Everything works. But the state transitions, they break and boom. Oh, crash. Much later. What can be wrong? And it took us some time to debug. And the developer came to the architects and said, I have a problem. It doesn't work. It crashes here, and the data is not saved, or the data is wrong, and I got wrong state in the database. I don't know what happened. And then we ask, did you list the reference in the reference description list? Oh, no, I forgot. And after the fifth, I decided I want to make sure a reference is contained in the return value of getReferences. But how? Okay, so I came up with a check, because when a developer adds a new reference, the least thing he or she will do is call get on the reference, because he wants to use the reference, otherwise he wouldn't have added it. And so in the get implementation of the reference, I put a check, which is a runtime check for the correct configuration of the referencing object. Okay, how's that implemented? The check iterates over all references and asks the reference description to check the reference. And if a reference says, well, I passed the check, it returns. Otherwise, if no reference has said, I passed the check, then it throws a configuration error, and the developer is reminded about what he forgot. And it says, well, this is not in reference description list. How is the check done? Well, the reference description, as you remember, has the member pointer. So we can apply the member pointer from the description to the given referencing business object, and then just check if it's the same pointer as the parameter given as this, and this is the pointer to the reference itself. Just a simple pointer compare. And if they are equal, oh yeah, we found the matching reference description entry, and then we are sure, hey, this reference is in the list, everything is okay. And that saved us so much time. Great. Okay. So, what was the most important takeaway from building the system is we built heavily on structural similarities to avoid boilerplate code. Make things which are equal look equal, but differentiate when necessary. So we have a find by ID method, not a find by division ID method, because the difference in the signature name would prevent generic code. So, for example, let's take the data container. Each data container of the 700 plus tables we have, 700 data container classes, each one defines a member primary key. And the primary key has the specific type of the data container. And so, if we want to fetch an object for which we have an ID and we know the data container type, we can just construct a generic select statement. Construct a select statement, we type it on the data container type we want to fetch. We build an expression syntax tree. We put a where condition onto the statement in which we assign, in which we use overloaded operator equal to build this expression. We put the division ID as the value, we bind it to the respective column, and then we just can execute the statement. And this is the generic code which is contained in every data access object. So we have a template for data access objects which works for all data containers. Easy as that. And as you have seen, we can use the ID type to select the proper data access object. And the resolver find by ID, we have seen the inheritance chain or the overloaded pattern just to select the correct data access object, which just executes this specific code, which is the same for every object. So all structurally similar things can be written as templates and simply be instantiated for every data container type. Done. Okay. Let's look at what we could potentially improve in the future. There are still a lot of things to do, and many of them are possible with C++ today. We could, for example, use unordered set and unordered map instead of set and map, but we found out that it's not always better in performance, so we're a bit reluctant currently. We could replace many classes from Boost, like shared pointer, tuple, stuff like that. We could replace recursive templates with variadics. We have seen the access definition, it's still a recursive template. You could just variadic archives it. Use parameter packs. We could remove necessity for type defs, because since we have decal type, we can calculate types as needed. We can use more auto to infer types and reduce the necessity to have the proper type defs in the proper places. But we have decided not to do it everywhere because it hampers readability. Because sometimes you don't know, just it's auto. Okay. And we want to keep sufficiently good compiler diagnostics, use concepts. We currently use concepts very sparingly, but we could improve on that. More type erasure. That's the thing we did very successfully in certain parts of the software where we register the services, and using type erasure there saved 8 to 12% in binary size of the affected DLLs. We could use ranges to return collections. We have just recently made the switch to C++20, so we could make full use of ranges in Microsoft world now today. But it's a bit difficult. We currently have very good ownership semantics. I haven't talked about the interface for returning collections because it would be another talk of 1 hour. So I wanted to spare you that. But currently we have a very good ownership semantics on that, and ranges might lose that. One thing I personally find very interesting would be to use more coroutines, especially to extend the select statement to return a data generator instead of the eagerly fetched collection. Currently we have like store and forward or fetch and forward, and for scalability it would be nice to have the option to stream a database query result. Okay, and then I got some wishes which are still impossible to do with C++ today, but I'm hopeful. I tried to const expr the get references method, but it currently depends on things not possible as const expr. Especially, I have not found a way to implement the completeness check as a compile time function, because at compile time I can't compare the pointers because this pointer is just not there. And I think it's currently not possible, but during the break, if someone has a good idea, I'm grateful. But reflection, which I often hear is an upcoming C++ feature, will make the check for the completeness unnecessary, because then I could just extract the reference members from the reflected class information, and I would not need to check if it's complete, because it would be complete because it's provided by the compiler. Okay, so let's wrap up the whole thing. Even C++03 allowed us to build a robust object-relational mapper, and I think we achieved all our goals. It was a bit harder than it would have been with C++20, with the features we have today, especially with the more mature compilers, which don't crash at the slightest imprecision of code. Yeah, but now in 2010 to 2013, we ramped up very quickly the mapping of the many tables. I don't know how many it were in 2010, but I guess it were like 500 and now 700. when we wrote most of the business objects, data access objects, and services, we would have benefited from Variated concepts, const expr. But now, yeah, there are nice additional improvements, but the pressure is gone. Because, yeah, we extend business object, yeah, okay, but we don't write 10 in a month. So, and looking back, we were able to compensate with good education for the developers and close supervision. So they always had some expert available to solve their problems and to keep them going. Okay, and also during the years which have passed since this phase, we have had only little problems with new language features, new compilers, new compiler versions. I remember I had to adapt code when the new compiler came up and the new standard features conflicted with others. They removed features. So code had to be reworked, but it was never a really big issue. But it's better to make many small steps than wait 10 years and then have to do a large step. So my recommendation is stay current. And last but not least, the object-relational mapper is still under active development. We still care a lot about performance, speed, RAM usage, ease of use, safety, good compiler messages, debuggability. There's something we can improve, and we will improve upon it. Yeah, and that's the end. Thank you for your attention.